so much as just kind of appeal to maybe some general notions of probability you might already have, and then apply that to some of the combinatorial problems that we've been approaching in a lot of different ways. So I'm just going to prove a little lemma today, and then we'll use that lemma a little bit more often in the future. So let's start by defining probability, not really carefully, but just by saying a probability P is a real number between 0 and 1 inclusive. That is, P is an element of the closed interval from 0 to 1. That's all I'm going to require for something to be called a probability. I'm just going to use this, and again appeal to some of your intuitive preconceived notions of probability, to define, again loosely define, sort of give you an intuitive definition of expected value. So I'm going to say that the expected value that some variable will have, so this would, if we were being really careful here, I would define a random variable and various types of experiments and processes, but I'm just going to kind of wash through that and say the expected value of some variable will have probabilistically weighted sum with each possible outcome, and I'll call each outcome xj, weighted by its corresponding probability. Pj, some variable x. All right, so I'm going to write this E of x is going to be the sum of all of the different possibilities, so ranging over this index, each probability xj weighted, each outcome xj weighted by its corresponding probability pj. So I just want to give you a rough example of this. So if I flip a fair coin 100 times, how many heads do I expect? Now, it's not how many heads will I see, or what's the likelihood that I'll get this or that. No, it's just what's the expected number of heads. Well, the way that I'm going to write this is I'm going to sum over all possible flips, and so I'm writing, well, let me write out expected number of heads in 100 flips, and this is going to be just a sum of j, the probability that I got j heads, times j. So I'd have to compute the probability that I get j heads and then multiply that by j. It's going to work out that this is equal to, well, 100 total flips times the probability of getting a head. So 100 times 1/2, and I expect to get 50 heads. So what happened here? Magic. Magic happened to get us from here to here. I know this is a combinatorics class, so it's a little embarrassing that I'm skipping a step like this, but this isn't what I want to focus on for this topic. So just to give you a rough notion of expected value, enough that we can use it to do what I want to do with it next. So if you have detailed questions about this, that's totally fair. There is a section in our book that deals with probability, and this does not take long to get through, but that's just not what I'm focusing on today. So I just wanted you to see a basic notion of expected value, and then if you see that it's a weighted sum, well, then I can multiply things through by constants and not affect anything. I can add and subtract these. It's going to be really well behaved. So let me now move back in time to the graph theory that we did. And I'm going to write down a few results that I'll be erasing soon. But then I want to leave their conclusion up top. So we had theorem 1, which was v plus f equals e plus 2, and this was for some graphs with certain conditions. The conditions we used were connected and planar, and it had to have at least one vertex. Then we had this theorem 2 that was 3f is less than or equal to 2e. And this, again, we needed a connected planar graph because we needed faces to mean something. And we did this for graphs with at least 2 edges. We put these together and we got this corollary. And the corollary was, again, in a connected planar graph with at least 2 edges, we had this little criterion, e minus 3v plus 6 had to be less than or equal to 0. And we used this criterion to check whether or not a graph was planar if we could verify by other means that it was connected and simple and it had sufficiently many edges. So this we spent a fair amount of time on, and something that I mentioned towards the end of that discussion, this is while we were still in physical classroom, was I mentioned the following theorem. So I'm gonna write this proposition down. So I'll be a little bit more careful here. This was the conclusion that we proved. Suppose G is a graph with at least 2 edges. So again, E is the set of edges, V is the set of vertices, and I'm going to have F is the set of faces. So then what we had was, if G was a graph with at least 2 edges, we had F faces and V vertices, then the minimum number of crossings was bounded below by size of E minus 3 times the size of V plus 6. And what we've done here is we've just said, well, check to see if this criterion holds. If it holds, great, we've got a planar graph. Or if it holds, then we don't have evidence that our graph is non-planar. Sorry, I want to be more careful there. If it doesn't hold, then we know there must be a crossing. If it doesn't hold for a connected graph where we have enough edges, we know there must be a crossing. So what we did was we removed an edge, and we just kept track, right? If I removed an edge and this criterion still does not hold, then I know that I still have a crossing in my graph. And I keep going, removing edges, counting the edges that I've removed until this criterion holds, in which case the graph must be planar. And sorry, I've misspoken again. The graph isn't necessarily planar, but in which case I know that I've had at least some number of edges taken out, meaning that the crossing number of the graph is at least the difference between that criterion and 0. That is the number of edges that I've removed at each step. This was the proof by Oracle. And again, this is reminding you of something we did in class. But I want to hold on to that, and I want to prove a new theorem. And this is what I'm going to call the crossing number lemma. So this is obviously, and the crossing number of G, again, is the minimum number of crossings under any redrawing. So remember, if I had like this graph here, this K5, I can draw it like this, but I could draw it with fewer crossings if I'm a little bit more careful, right? So if I'm really careful, I can draw it with fewer crossings. What is missing? I've not connected this to that. So then I've only got 1 crossing here, whereas here I've got 5 crossings, right? So the idea is this gives me a lower bound on the crossing number of a graph, based on just its number of vertices and number of edges. So I want to use this to prove a more powerful crossing number lemma that we'll be using in the future. So crossing number lemma, this is what I will call the crossing number lemma. Even though this is another result about crossings, this is what I will call the crossing number lemma. And that is if E is greater than or equal to 4V, then we have the crossing number of G is bigger than or equal to, with a squiggle, E cubed over V squared. So there's a constant here. I'm not going to optimize for constants. Now what I want to do is I want to apply expectation to both sides of this graph, both sides of this proposition. And what I'm going to do is I'm going to be randomly considering induced subgraphs of my original graph. So what I'm going to do is I'm going to pick P between 0 and 1. And actually, for this theorem to work, I'm going to pick between 0 and 1 inclusive. We're gonna fix a value of P in a little bit, but in particular, I'm going to pick P between 0 and 1 so that the expressions that I'm about to write make sense. So I pick P, and then I consider a random induced subgraph H of G. And how do I do this? I say that each vertex survives with probability P. So, I've got whatever my original graph is, G, and it has some things happening. How do I find my subgraph? What I'm going to do is I'm going to go to each vertex and it will survive with probability P. Now I said this is an induced subgraph, so if these two vertices survive, then by default that edge survives. But if either vertex goes away, then that edge goes away. Similarly, if these 4 vertices are here, these 2 edges survive, but depending on the configurations of the other vertices and edges that have left or have stayed, this may or may not induce a crossing in the new induced subgraph, right? So let's compute the expected number of vertices first. Well, the expected number, and I'm going to call this expected number V sub H. So I'm looking at the expected number of vertices in our subgraph. Well, this is going to be, if each vertex survives with probability P, I'm just summing over each vertex surviving with probability P. So that's just the sum over all the vertices weighted by P, or P times the original number of vertices. Next, let's look at the expected number of edges. Well, the expected number of edges in the subgraph, it's going to be looking at every edge and seeing if what happens. Well, in order for this edge in my old graph to survive in the new graph, I'm going to need both vertices to survive. And what's the probability that 2 vertices, specific vertices, survive? Well, each one survives with probability P, meaning both of them survive with probability P squared. So this is going to be P squared size of E. Now the next piece is a little bit delicate, and I've already alluded to it. But what's the expected crossing number of H? And I'll give you a second to think about this. All right, so in these cases, I could exactly compute the expected value. But here, it's a little bit tougher. Crossings, remember, are a little bit less... they're a little bit harder to get our hands directly on. So what happens, if there's a crossing that it's necessary in any drawing of my graph G, in order for this crossing to survive, I will definitely need those 4 points to survive. So I will need p to the fourth, because I'll need p times p times p times p, 4 factors of p, times the crossing number of g. But the tricky part here is just because these 4 vertices survive and they were involved in a crossing in G does not mean that they will necessarily be part of a crossing in my new induced subgraph. So if enough other edges and vertices had popped away that I could redraw this graph without a crossing, then that crossing might disappear even though all 4 of those vertices remain. What this means is this just gives me an upper bound for the crossing number. Okay, so I don't know how many crossings I'm going to get in my new subgraph, but I know it's going to be no more than, or the expected value is going to be no more than p to the fourth times the crossing number of g. All right, now what I want to do is I want to write this down. So let's suppose that I've got some graph G with at least 2 edges. And you recall we got to relax some of these things. Just stepping back for a second. This I didn't necessarily need planar or connected because, well, obviously, I wouldn't need planar. I wouldn't necessarily need connected because I could just connect disconnected components and it would help me and not hurt me. That's something we discussed again in class earlier, so stepping through that quickly. But now I've got a graph with at least 2 edges. I'm going to write this down, and that is the crossing number of G is bounded below by the size of E minus 3 times the size of V plus 6. And what I want to do now is I want to take expected values of both sides. And what does it mean? Well, the expected value of the crossing number of G is just the crossing number of G. But what I mean is I'm going to take the expected value of the random subgraph. Okay? So when I take the expected value of the random subgraph, this process of expectation is linear, so I'm not going to have anything funky come out of here. Okay? But now the expected number of the crossings in H, that's my new random subgraph, is the expected number of E sub H, V sub H, etc. Okay, so this is the expected value coming from my subgraph. And let's write down what we know. Well, this, on this side, is, so the expected value of the crossings in H is bounded above by p to the fourth times the number of crossings in G. And this side is going to equal the expected value of E, which is p squared E, minus 3 times the expected value of V, that's 3p times the original V, plus the expected value of 6, which is just 6. Okay, 6 is just 6. All right? So now if I compare the left-hand side and the right-hand side, what I'm going to do is I'm going to get, let me just put these together, I'm going to get the crossing number of G times p to the fourth, and I'm going to divide both sides by p to the fourth in a second here, is equal to p squared, not equal to, is greater than or equal to p squared E minus 3p V plus 6. Well, if it's greater than this plus 6, it's also greater than that without the plus 6. So I'm going to just, let's see if this is on the screen still. I'm going to just get rid of that plus 6. So this is greater than p squared E minus 3pv. All right, it's certainly greater than this. This is greater than that. And now I'll divide everything by p to the fourth. And I'm going to get the following. Let's tilt down a little bit here. I'm going to get that the crossing number of G is bounded below by, well, I've got p squared size of E minus 3p size of V over p to the fourth. All right? And now what I'm going to do, and here's where kind of the magic happens. I picked, remember, that E was bigger than 4V. And if I want to be, actually, if I want to be pedantic, let me pick e to be strictly greater than. I don't think it'll actually matter because of the way I've got the constant set up. But let's set e to be strictly greater than 4v. And now if I plug in, because e is greater than 4v, that means that p, I can pick p to be whatever I want as long as it's between 0 and 1, and this statement will still hold. I'm going to pick p to be 4v over e. If p is 4v over e, this is a number between 0 and 1 by that claim. And if I plug in 4v over e into this thing here, I'm going to get what? Well, 4 squared gives me 16, and then I've got v squared over e squared times e. This is going to give me v squared over e squared times e gives me v squared over e. No, sorry. Have I made a mistake here? V over e. Well, let's just keep going. Maybe it'll work out just fine. So this is 16 v squared over e. I forgot about my denominator. Minus 3 times p is going to be 4. And then I've got, again, what? Well, v over e times v, so v squared over e. And then on the bottom, what do I have? Well, on the bottom, I've got p to the 4th. So I've got 4 to the 4th. Well, 4 to the 4th, that's 64 times 4, which is 128 times 2, which is 256, times what? Well, now I've got v to the 4th over e to the 4th. We're getting kind of low here. And we're kind of needing boots. This is getting deep. But now we can start canceling things. So I'm going to take CRG bounded below by, well, I've got 16 minus 12. What's 16 minus 12? It's 4. 4 over 256, that's the same as 2 over 128, or 1 over 64. I've got 1 over 64. Now, v squared, both of these numerator terms are the same as far as v and e are concerned. But they have the same number of factors of v and e. So v squared divided by v to the 4th is going to give me, well, I'm going to end up with something over v squared. And then I've got 1 over e on the numerator, and I've got 1 over e to the 4th on the denominator, and that, putting those together, gives me e cubed. So I've got 1 over 64 e cubed over v squared, and what do you know? This is precisely what I claimed. I claimed the crossing number would be bounded below by some constant times e cubed over v squared. Now the constant that we've gotten from this derivation is 1 over 64. That constant is related to primarily my laziness as a presenter, but it's related to our choice here. Now I do want to say a word on our choice e bigger than 4v, because this kind of comes out of nowhere. What I want to say is, if, and this is partially why I presented it this way, if I don't know about this condition yet, and I'm just seeking some lower bound for the crossing number, asymptotic lower bound for the crossing number, I could follow this random subgraph construction, and I would get to this point here where I have to choose my p. Normally, in a lot of asymptotic type of problems, what I want, if I'm adding or subtracting some pieces, is for this piece and this piece to contribute the same asymptotically, or to have the same sort of big O, or big theta, I guess would be a little bit more appropriate there, but to have the same order of magnitude of growth. That way, each piece of information is being used sort of in with equal weight. If you tell me 2 useful pieces of information and I ignore one of those pieces of information, I'm probably not doing things as efficiently as I could. So here I want to use both pieces of information, and what I mean by piece of information, I mean these are saying something about the size of the crossing number of my graph, right? So I want these to be comparable in size, so what I want is for p squared e to be roughly the size of 3PV. So if I just take a second and solve these, I'm going to get that P is equal to 3V over E. And that's great. But if P is equal to 3V over E, then this numerator becomes 0. And that's not super helpful. So I want the numerator to be something positive, but on the order of V over E. And so that's where we got 4V over E rather than 3V over E. And as you tweak this constant, if we were to make this 3.1V, we'd get a different constant here. So that's why, we've specified one constant, as you'll see, that's just useful, but we've sort of hidden the other constant. Another thing that I want to say is this doesn't have any randomness in it at all. Okay? I've really just used the language of randomness and probability to hide that we are averaging. So this whole thing is a set of averaging operations, but you will often hear about random graphs or probabilistic methods, and those can involve true randomness, but oftentimes when someone says that they've proved something by random methods, what they mean is they've considered all possibilities, in this case all possible subgraphs, and they've set sort of a level playing field probabilistically of each subgraph happening. And oftentimes in a probabilistic argument, you show the probability of something occurring in a random setting is positive. That's just an existence proof. In this case, we're doing something more powerful, but also way simpler. And some people might even say this isn't a probabilistic proof, and that's fine. But the idea is that you see how we can use the language of probability to prove something deterministically. Okay, we've said, oh, this happens in a random sense with this probability. That's just a euphemism for, if I consider all possible subgraphs, how many of them will have this edge, how many of them will have this vertex or whatever. And that all comes out in the wash because expected value is summing over those things equally. So I hope this made some sense. At the end of the day, this is the big result. We're going to be using this throughout the remainder of the semester. And what you should take away from this is we had this little proposition from earlier in the semester. We proved this in the graph theory unit. And what I told you then was that I was going to beef it up by using it as the kernel of some bigger argument. And here, this whole argument relies on this. This relied on the stuff we did with Euler's formula and the Wiener dog ear theorem. So all of this is a bunch of little ideas that are growing together and getting bigger and bigger and bigger. And while this might not seem so beautiful on its own, this is a 3 here. I think my marker kind of erased that. While this might not seem like much on its own, we can prove very powerful results with this elementary theorem. All right, thanks so much. Talk to you again soon.